Now let's switch gears and talk about some scales to measure temperature. So we talked about the zeroth law and we said it defines temperature. How do you measure temperature? Well, you measure it with the thermometer. And everything. I think everybody has seen the thermometer and probably has used it as well. Quite helpful, especially if you ever have a fever. Um, so thermometer is how you measure temperature. What are the different units that you can measure temperature? You can measure it in degrees Celsius, Fahrenheit, or Kelvin. Americans use Fahrenheit for some reason. The rest of the world, I think, uses Celsius. Don't quote me on that, but that's what it is. The Kelvin is used mostly by the scientific community. So there's three different scales. It's very easy to convert between them. You can look that up. It's extremely easy, but I will show you one main conversion, and that's if you want to go from, you know, if you want to go to if you want to convert from Celsius to Kelvin, then there's a little formula you can use. It's 273.15 plus temperature that you have in degrees Celsius. So what it's saying is if you want to find your temperature in Kelvin, all you gotta do is add 273.15 to the temperature you have in Celsius. Straightforward enough. Let's talk a little bit more about the Kelvin scale, give you an idea of what it is. So the Kelvin scale runs from 0 Kelvin, and it goes on to very, very high temperatures as well. So the constraint we have is actually here. This is why I didn't draw a shaded circle. I drew a hollow circle for a reason. We have a constraint here. We can't get to 0 Kelvin. We'll talk about that later on, why that's the case. And we can go to very high temperatures if need be. So this is why it's called the absolute scale, because all values of temperature in Kelvin are greater than 0. It is not possible physically to have a temperature that's 0, let alone be negative Kelvin. So that just doesn't make any sense. So now, why can't we have 0 Kelvin? I'll give a short quantum mechanical explanation. Hopefully it helps. If it doesn't, we'll build on, and maybe thermodynamical sense will help you more. So from quantum mechanics, we know this idea of Heisenberg's uncertainty principle. So what it really says is that you can never measure with precision the momentum and the position of a microscopic particle. So in a particle where quantum rules apply, something that's the size of an atom and even smaller, where you enter the quantum world, that's really going to help us define 0 Kelvin, why we can't get there. And at that very small scale, Heisenberg's rule states that you can never measure these two quantities simultaneously with a lot of precision. If you measure, momentum with a lot of precision, your precision and position is going to change. So what it's saying is, if you know how fast an electron or a subatomic particle is going, then you don't really know where it's going. You can't really tell anything about its position. If you know about the trajectory of a subatomic particle, then you don't really have its speed measured in precision. That's what the Heisenberg uncertainty principle says. That simple little fact that these two can't be measured simultaneously, it places a great amount of restrictions in the world around us. One of these is why we can't get to 0 Kelvin. Well, we know that temperature, some of you might not know this, but temperature is the reason why molecules have kinetic energy. So if you know, kinetic energy is 1/2 mv squared. So the reason why molecules are moving around in a system is that because they have some sort of temperature associated kinetic energy, so they're always moving around. At 0 Kelvin, what happens is the kinetic energy essentially becomes 0 because the temperature is 0. So the kinetic energy which you'll drive later on, which I'll drive later on, how it depends on temperature. When we start talking about the ideal gas law in a little bit more detail, you will understand why EK, or the kinetic energy, is so dependent on temperature. But for now, just note that temperature is given by it defines kinetic energy. In the cartoons we've seen that the light fire under a cartoon and then they're running super fast. So that's kind of the same idea. You fire up a gas and the gas gets all panicky and it starts speeding up. Okay, we know what happens if we heat the system. What happens if we cool the system and let's say we get to 0 Kelvin? So we're cooling the system slowly, slowly, slowly. We're taking away that fire. It's kind of like freezing something, right? You're getting colder. It's almost as if you're freezing that. You're reducing motion. That's why matter gets more compact and condensed as you get colder and more expanded as you get warmer. But that's a different discussion. So as you get colder and colder and colder and towards 0 Kelvin, what happens is that molecules stop moving. At a certain point when you hit 0 Kelvin, you should essentially see that since EK is 0, that would imply that the velocity of these particles is 0. Mass isn't randomly going to become 0. We know from energy conversation that mass and energy are interchangeable. So the mass can't magically become 0. It has to be the velocity becomes 0. That means these particles aren't moving. So if these particles aren't moving, their momentum is also going to be 0, right? They're not moving, they're in one spot. Okay, if you know that they're not moving, they're in one spot, then essentially you would be able to tell something about their position. You would be able to define these two quantities simultaneously with 100% accuracy. That is against the laws of quantum mechanics. It doesn't happen. It defies Heisenberg's uncertainty principle, hence why we cannot reach 0 Kelvin. We absolutely cannot afford to see molecules have zero motion. Okay, they always need to be moving. We'll discuss the thermodynamical definition and the answer to this is soon enough as well. Why? But for now, this is kind of an intuitive reason as to why you can't hit that 0 Kelvin part. It's because your molecules lose motion, right? Our laws start breaking down at that point. So, moving on from a grim discussion, the grim discussion of why we can't get to 0 Kelvin. I think it'd be extremely cool if we could. All sorts of magical things would happen. We would get perpetual energy machines, at 0 Kelvin. It would be awesome. Just doesn't happen. And if you ever were to discover a way to get there, I would say that you would become a very, very, very successful person. Okay, so now moving on to state variables, we'll revisit them and we'll talk about equation of states.